So if we have mixtures with no common ions, then we just do it separate. Oh, okay, yeah, it's not coming up. Mixtures with no common, we just do separate ice tables. But when we do have common ions, then we do it differently. It depends. With common ions, we'll just do it stepwise. Unless we have a special case. In which we could use the Henderson-Hasselbalch. That was the question earlier. Henderson-Hasselbalch equation, which is a buffer. Of course, these are special cases. We'll talk about that. And then we have common ion problems where we'll have to do it simultaneously. Just like before. So what's kind of new here is this Henderson-Hasselbalch equation that we can use. So let's look at mixture with common ion. So mixtures with common ions would be like HCl plus sodium chloride. When we look at both of these here, they'll have the chloride as a common ion. And what we try to do is we'll just try to do it stepwise. And so normally when we have soluble salts, we'll start with those. So soluble salt, sodium chloride. And let's go with 0.1 molar. We have to have significant concentrations of both. And so we'll do 0.1 molar each. And so I'll just break this up into steps. So step one would be 0.1 molar sodium chloride. And sodium chloride, being a strong electrolyte, dissociates completely, or we assume it to be. We'll just say K is very large. And for all strong electrolytes, we assume K is very large. Assume for all strong electrolytes. Okay, so initially we have this. We'll just assume none of it's dissociated. And the change is going to be complete. So we end up with 0 molar, 0.1 molar, 0.1 molar. And just say we have complete change because our K value is very large. Okay, then we'll go on to step 2. Step 2 will just drop down the common ion. So step 2 will be HCl plus water, or Ka. Now what we do in these mixture problems, we want to react the strongest acid. It doesn't have to be strong, but just the strongest acid present with strongest base present. So the strongest acid present is going to be HCl. The strongest base present is just going to be water. Chlorides is a weaker base than water. So it's going to be HCl and water. This is going to produce hydronium and chloride. And K is going to be, this is Ka for HCl, acid plus water. This is very large. So initial change, equilibrium. And so what we'll do is the sodium, this is the end of the line for the sodium. However, the chloride drops down to the next step. So we're not done with chloride yet. And so what's happening with the chloride? The chloride is dropping down as common ion here. And so this HCl is going to be 0.1 molar. We're going to assume nothing's reacted with the HCl so that we have 0 hydronium, but the chloride is going to be 0.1 molar here. That comes from step 1. And then the change is going to be complete because when we have very large K, it's going to just be minus 0.1 molar plus 0.1 molar plus 0.1 molar. Okay. And so we end up with 0 molar HCl, 0.1 molar hydronium, and 0.2 molar chloride. Now, if I was interested in the pH, would I do step 3? No, I would not do step 3. What is step 3? Wait. Step 3 is H2O liquid plus, we take the next in line, next hydronium contributor in this case. I was interested in pH. It's going to produce hydronium plus hydroxide. If I was interested in pH, I'd stop here because this is 0.1. And the max I'm going to get is less than 10 to the minus 7. We're not at 10 to the minus, actually in this case it's going to be quite small, 10 to the minus 13 or so. So we expect very little contribution of additional hydronium here. So if I would stop here for pH, continue for inventory. If we're going to inventory the solution, then we need to continue down. And it's just a stepwise technique. So what we're going to do is drop this from step 2 to step 3 here, the hydronium, and see how much additional hydronium I'm going to get from water. And so what we'll assume is no hydronium has been produced from water. Kw is 1.0 times 10 to the negative 14 here. And we just continue, change equilibrium. So we're going to get a little bit more hydronium from water, but that little bit is going to be way less than 10 to the minus 7. So this is 0.1 plus x. It can't be as big as 10 to the minus 7 because we already have lots of hydronium in there to begin with. And so this is just equal to hydronium times the hydroxide concentration, and then we'll solve for x. 0.1 plus x times x, and then we'll use the simplifying assumption. This is going to use 0.1 x, and then x is equal to 10 to the minus 1.0 times 10 to the minus 13. And then we have to justify our simplifying assumption by determining a percent change. The percent change is 10 to the minus 13, which is the change, or the initial, which is 10 to the minus 1 times 10 squared. And so this is going to be 10 to the minus 12, 10 to the minus 10%. 10 to the minus 10% is good. It's less than 5%. And so the simplifying assumption is so good in this case, I wouldn't even bother doing the quadratic, as I get the same answer. And so here it's going to be 0.1 plus, how many zeros do I need? I need 12 zeros after the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1. And so the change was so small, it's even very hard to register. 3, 6, 9, 10, 11, yeah. Molar. And then x is just 1.0 times 10 to the minus 13. Okay, so 10 to the minus 1 times 10 to the minus 13 is going to give me 10 to the minus 14. So the k checks out. So k is equal to 1.0000 times 10 to the minus 14. And so that checks out. All right, we would do this if we're determining inventory. So when we're determining inventory, we just go down the line and see, okay, what happens to chloride? Well, actually, sodium chloride ends up, formula units ends up at, molecules, or actually we can't call these molecules. Just we end up with 0 entire ion pairs. HCl molecules, we end up with 0 molar. Chloride, this is the end of the line for chloride, that's at 0.2. Hydronium, we end up here for hydronium, and hydroxide, we end up here. pH of this is going to be 10 to the minus 1, so pH is going to be 1.00. It wouldn't have made much difference had I done step 3 or not. as far as pH is concerned. So pH is the native log of the hydronium ion concentration, which is 0.1000001, which is going to come out to 1.0. Now, how many sig figs am I allowed here? Well, this is only doing 1 sig fig, so this is actually 1 sig fig here. But it goes beyond that. I could carry extra. The extra ones I'll just subscript. All right, so if I have a beaker that's labeled 0.1 molar sodium chloride and 0.1 molar HCl, what will I find inside this beaker? Okay, inside the beaker, this is the inventory part that we have. So inventorying this, sodium concentration will be, we had it up here, 0.1 molar. The chloride concentration will be up there, 0.2 molar. The hydronium ion concentration will be 0.100 molar. And the concentration of molecules of HCl is 0. We have, I don't know, I mean, we could put that here. This is 0 molar. All the HCl is broken up, and then we have some hydroxide in there. 1 times 10 to the minus 13 molar. And so that would be the inventory for this. You could have done this without doing. This is just showing the methodology that we'd use in Chem 1B. In Chem 1A, you would have just combined everything. Would have been fine. All right. Let's look at another example here. And there's going to be a difference now with the let's see. Let's go with something like nitrous acid, and let's pick another one. Let's do nitrous acid and acetic acid. What's the common ion between these two? The common ion is either going to be H plus or hydronium. Let's do the common ion here. All right, now what we do is we try to start with the largest K, because I'm going to always try the stepwise approach because it's the easiest. So we start with the largest K value and then give this a go. So we need to know the Ka for HNO2 and the Ka for acetic acid. The Ka for acetic acid, I know that one, which is a 1.8 times 10 to the minus 5. But nitrous acid, I have to look that one up. It's 5.1. Can somebody read that? Times 10 to the minus 4? Is that correct? Bottom left? Or near the bottom left? 5.1 times 10 to the minus 4? Yes. Okay, thank you. All right, which one's bigger? Nitrous acid's bigger, so we'll start off with nitrous acid. So my step one is going to be nitrous acid, HNO2, and I'll take the strongest base present. The strongest base present is just water. So nitrous acid plus water. This is going to yield hydronium plus nitrite. And we know that Ka will be the hydronium ion concentration times the nitrite concentration divided by the nitrous acid molecule concentration. This is going to equal 5.1 times 10 to the minus 4. So we'll do the same thing. We're going to start off with 0.1 molar concentrations of each. Now, what if I had a lopsided mixture? Like, for example, I had a lot more acetic acid than nitrous acid. If I had a lopsided mixture with a lot more acetic acid, I'd still start with the biggest K. And so initially I'm going to have 0.1 molar. And since we're doing this stepwise, I'm not going to worry about the hydronium from nitrous acid and the hydronium from acetic. We're just going to assume that nothing's hydrolyzed, including step 2. And so this is going to be minus X plus X plus X. And so I'm going to have 0.1 minus X molar, and then X molar here. And so this is going to give me X squared over 0.1 minus X. And then I go ahead and try the simplifying assumption. This is just going to give me X squared over 0.1. And then X is going to equal the square root of 5.1 times 10 to the minus 3. Let me just calculate that. 10 to the minus 5. So I have 5.1 times 10 to the minus 5 minus 4. Minus 4 times 0.1. Look at me. 5.1 times 10 to the minus 5. And then we'll take the square root of that. So I come up with X is equal to 0.00714. I'll just carry some 1414. A few extra digits. And then I'll do the percent change. This comes out to a 7% change, unfortunately. Because if I call this 0.100, right, then it's 7 parts out of 100. And so 7 percent change. The 7% change is too big. And so let's get this into quadratic form. This is going to be X squared minus 5.1 times 10 to the minus 4. I'm going to write this in decimal form. 3 zeros and a 5 1. X. And then plus 4 zeros after the decimal, and the 5 1 is equal to 0. All right, so now I need to go to quadratic solver. And for homework, I would just use the quadratic calculator online or something. So that's 1. And this was 5.1 times 10 to the minus 4, and 5.1 times 10 to the minus 5. And calculate that. I made a mistake because I'm coming out imaginary. Oh yeah, negative. Calculate that. Thanks. Still coming out imaginary. Oh, C, that's negative. For that. If you're coming out with imaginary numbers on the test, then it's probably just a simple sign error. I know some people were coming out with imaginary numbers. All right, so the X is 0.006890. That's quite a bit different than the simplifying assumption. With the simplifying assumption, we got 0.0071. Without the simplifying assumption and using the quadratic, we came out with 0.0068. So the simplifying assumption introduced quite a lot of error into the calculation, and that's because of the 7% change, which is quite big here. All right, I need some more pages here. All right, so what we want to do is we want to calculate our equilibrium concentrations here. So go ahead and do that. 0.100 minus 0.006, this is going to come out to 0.0993, 0.093, 110. And the hydronium is just going to come out to 0.00689. And the NO2 is 0.00. I'm already carrying extra digits, so I'm not going to carry the extra 0. 689 molar. And so let's double check our K value here and see what that comes out to. So we'll do 0.00689 squared divided by 0.09311. And it comes out to 5.098 times 10 to the minus 4. It should be 5.1. So 5.098, that'll round to 1. That's close enough for us. So this checks out. Okay, now we're going to go to step 2, which is going to be the next biggest K value, which is going to be acetic acid. We'll do step 2. So this is the same procedure. When we do stepwise, we'll just carry down whatever common species there are. So we've already done this kind of thing here. We're going to carry down the hydronium, but for the nitrous acid molecules, it ends here, and for the nitrite, it ends here. But the hydronium is carried down into step 2. And for acetic acid, I'm just going to write it using the abbreviation HAC for acetic acid plus H2O liquid. It's going to produce hydronium plus acetate. Okay, again, we're going to assume that none of the acetic acid has hydrolyzed, but we're going to have how much was that? 0.00689 molar. From step 1. And 0 molar acetate here. The change is not going to be so big because of the common ion effect. It's kind of Le Chatelier's principle. The more product you have, the more it tries to shift it back or resist that change. And so we end up with 0.1 minus X here, molar, and then 0.00689 plus X, molar, and then X molar here. So the Ka, which is 1.8 times 10 to the minus 5, is going to equal the hydronium times the acetate divided by the acetic acid molecule. concentration, which is going to be 0.00689 plus x times x divided by 0.1 minus x. So I'm going to just go ahead and try the simplifying assumption here. But I have a choice for simplifying assumption. I have these two binomials here. I can make x less than 0.1. That'll clear the bottom binomial. And I have to make x less than 0.06. We'll try that. 68. So we're just going to say x is much smaller than 0.0068 using the simplifying assumption. And if that's the case, then we're going to get 0.00689 plus x, which is that. 0.0689. 0.1 minus x, which is 0.1. This is times x. So what will x come out to here? So I'll do 0.1 times 1.8 times 10 to the minus 5. Divided by 0.00689. And that gives me 0.000.261. All right, so the percent change for the denominator is okay, because this, in the denominator, this is 0.100. So this would be a 0.2% change in the denominator. But in the numerator, it's not, it's going to be a much bigger percent change. And so let's look at the bigger percent change here. The percent change is going to be 0.00689 is the initial. So this will be x, which is 0.00261 divided by the initial, which is 0.00689 times 100%. So let's divide this by 0.00689 times 100. 3.79%. Is 3.79% acceptable? It's acceptable. I mean, that's less than 5%, so we'll just go with that. You use the simplifying assumption to save time. We're sacrificing some accuracy, though. I mean, that's getting close to 4%. So we're sacrificing some accuracy to save a little bit of time, which is all right. Just do that. And so we're going to get 0.1 minus 0.000261. This is going to give me 0.099739. And then over here, I'm going to have 0.00. What's that? Not 0.00. Yeah, what was it? 0.00689. 689 plus 0.000.261. And this is going to come out to 0.00. Okay, what is that? 7. Oh, I better do it. I'm just going to add it in the calculator. A little less prone to making mistakes. 7151. And this will be 0.00261. Mullet. Let's check my K value here. So it's 0.07151 times 0.000. 261 divided by 0.099739. 0.099739. This comes out to 1.871 times 10 to the minus 5. It's supposed to be equal to 1.8 times 10 to the minus 5. Are we close enough? It depends. You know, I would start to worry because this is looking more like 1.9. But we have to recognize that we had a 3.79% error there. So if I don't know, is this error here due to using this simplifying assumption? Or is this error because I made some other mistake, a real mistake? I would want to eliminate the possibility that I made a real mistake, because then you start thinking, okay, did I make a mistake in the calculation? Maybe I got the numbers mixed up or did something or screwed it up. And so I just need to know, is that because of using the simplifying assumption, which is good and close to the limit of acceptability? And so what I'm going to do is I'm going to just compare, because I'm worried about this. It's a little off. Acceptable? Maybe. Yeah. And so that's the question. Maybe this is perfectly acceptable because we're still within the 5% limit. And so to answer this question, I'm going to solve this without using the simplifying assumption. So let's get this in quadratic form, which is going to take a little bit more work here. So this is going to be 0.0000 quadruple 0261. Okay, minus 0.000261x is equal to, over on this side, I'm going to get 0.00689 x plus x squared. All right, let's get all the terms on one side. So this is going to be x squared. Okay, then I got to add a 0.00261 to a 0.00689. So I'm going to do that here. 0.00261 plus 0.00689. And then 0.07151. Let's already get that additions. So this will be plus 0.00751 x minus 0.00261 is equal to 0. All right, now I'm going to go back to the quadratic solver. I wouldn't do this if I didn't have the quadratic solver, because it would just take too much time using the quadratic equation. So my B is 0.00751, and my C is 0.00261. Calculate it. Oh, I forgot the negative. It came out imaginary. All right, now I have an x value here. The x is equal to 0.00266. So by using the simplifying assumption, we came up with an x value of what was it? Did I get it wrong again? 0.00266. Let me see if I screwed something else up. Anybody else get a different answer? Well, it looks like I inputted this correctly. So I might have made a math mistake. So 0.00266, is that? God. I can't, I must have made a mistake somewhere because take a look at the difference here. I have a 00266 and I have a 000261. So I can't be that far off. It can't be that different, you know, using the simplifying assumption. But maybe it is. Well, what did you get for your answer?
I got 2.514 times 10 to the negative 4.
You got 2.514 times 10 to the negative 3?
4.
4? Okay. That sounds more reasonable. Was your quadratic equation the same?
I didn't look at it. It's like different components.
Let me recheck my quadratic equation. Solved it. Oh, I know what I did. Gosh. My quadratic equation is totally wrong. It's totally wrong. Let me redo it. I was using something else for k. It's 1.8 times 10 to the minus 5. Which I don't want to do this in scientific notation because it takes me longer to plug it into my calculator. So I'm going to do quadruple 0.18. Okay. This is equal to 0.00689 plus x times x. Divided by 0.1 minus x. Okay, now this should work out a bit better. So 0.1, 10 minus 1, so this is going to be 5 zeros and a 1/8. Minus quadruple 0.18x is equal to 0.00689x plus x squared. Okay, let's get this into quadratic form here. So this is plus quadruple 0.18, which would be 671. $698. Maybe I should have left it in scientific notation. Let me double check my math. Yeah, okay. All right, let's try this one now. This should be 006908 and quadruple, or actually quintuple 0, 1, 2, 3, 4, 5, 1, 8. This should be negative. Yeah. So you had it right. So just 0.000251. Just carry one extra digit. Okay, so that came out to 251 versus a 261. Not a huge difference, but let's see what difference it makes in the concentrations here. So I'll redo these concentrations here in green. So I'm going to have 0.1 minus 0.000251. I'll just add another 10 to it. This is going to come out to 0.099749. 99749. Try that. 251. This should come out to 0.007141. The addition. And this is going to come out to 0.00251 molar. And so let's try these numbers and recalculate our K value here. Is 7.9 times 0.007141 times 0.000251. Okay, this comes out to 1.796 times 10 to the minus 5. All right, now this rounds to 1.8. It's very close to 1.8, so this looks good. So the reason this was off, acceptable, the answer would be yes because of the SA. Was still below 5%, but it was getting high. It was 4%. About 4% change. And so that led to a little bit of error. And so, yeah. All right, but whenever we do this, what do we have to check? Which is something I didn't check up here because we're in the habit of not checking this. Let's go back to the previous problem up here. And the previous problem is I look at step 1 and I go to step 2. And take a look at what happens from step 1 to step 2. I double the 0.2 molar. I double the chloride from 0.1 to 0.2 molar. Do you see that? If I double the chloride concentration, shouldn't Le Chatelier's principle say we shift this back to the left? Doesn't Le Chatelier say that? If I double the product concentration, I should shift it to the left. However, I don't shift this because even though I doubled the concentration here, it doesn't shift it back to the left. The reason it doesn't shift it back to the left is when we have Ks that are very large, these are one way. And these are not going to be perturbed. And so I doubled this. And so it should have screwed up equilibrium step 1, but it didn't because this is a one-way reaction. I have to check this for each step. So then I go from step 2 to step 3, and I increase the hydronium. But did I increase the hydronium significantly? No, I increased it negligibly. And so there are two factors here. In going from step 2 to step 3, the increase in hydronium was negligible. So the impact on step 2 would be negligible. And number 2, step 2 has a K that's very large. So even if the change were significant, it still wouldn't have any impact. Does that make sense? So you have to check this. So there's no impact on the prior steps here. In going from step 2 to step 3, and nothing. Yeah. However, here we started off with 0.689, and then we jumped up to 0.7141. 0.7141. We'll just use the quadratic since we did that. Was that a significant change? So one way to check if it was a significant change is we could do the K value. So for example, if we did the K value with the new hydronium concentration of 0.07151, that's the total hydronium for steps 1 and 2. 1 and 2. I haven't included step 3 yet. Times this 0.00689 divided by this 0.09311. What does that do to our K value? And so I'm going to have 0.071. Is it 5.1 or 4.1? Sorry. 4.1. Mistake. We'll use the one from the quadratic, or you could use the one from the simplifying assumption too. So 0.00741 7141 times 0.00689 divided by 0.09311. And I get a K value that comes out to 5.28 times 10 to the minus 4. Now, the K value is supposed to be 5.1 times 10 to the minus 4. So this is the K value that was given, 5.1 times 10 to the minus 4. So is that acceptable? It comes out to 5.3 versus 5.1. Is that okay, or was that a significant change? It was 5.1. Remember, it was 5.1, but we perturbed it. So the equilibrium was perturbed. So we have two choices at this point. One, we could say it's negligible. So we could say going from 689 to 715 is negligible. Would you say that's a negligible change, going from 689 to 715? What would that percent change be? So 715 minus 689 divided by 689 equals divided by 689. That's a 3.77% difference, percent error. And so this is a 3.7% error, or roughly a 4% error. Versus what it was before. So the point I'm getting at is this. We have two choices. Choice one is what we should do. What we should do is, that's going to upset this. So if I increase the hydronium concentration, then that says, the Chatelier's principle says we have to shift this to the left. If we shift it to the left, we have to recalculate the new equilibrium concentrations. But we have a problem with doing that, because if we did that, what are we going to be in? We're going to be in the Chem 1B, the loop. Yeah, the endless loop, the infinite loop. Therefore, we shouldn't try that. We're not going to do Le Chatelier's reset of this. Instead, what we should do is we should solve these simultaneously. This has to be solved simultaneously. So in other words, step 2 perturbs step 1. Therefore, simultaneous equilibrium. So what we need to do is we need to come up with a common hydronium. We did. So we set it up similar, except there's one other equation that has to be factored in. And what's the one other equation? The water. But do you think water is going to add much? No. So we might be able to get away with ignoring water. In fact, we probably can get away with ignoring water and then just do two ice table simultaneous like we did before. All right, so when does this happen? When this happens is if you take two weak acids that have kind of similar K values, or you take two weak bases that have similar K values, then you're going to run into this problem. If we have one strong and one weak, we don't run into this problem. One strong and one weak works out nicely stepwise. But two weak ones are not good, not easy to do. Unless we have this scenario. This is a special case. Well, actually, let's take a look at some more mixtures before we get in. And that's when we have Henderson-Hasselbalch. With the Henderson-Hasselbalch, we're going to have a weak acid. And it's going to be a weak base. But the situation with the weak acid and the weak base are their conjugate pairs. Or we'll have a weak base B and its conjugate. Actually, the plus should go on the B. Because now it's using the lone pair that it originally had as a bonding pair. And so this is the weak acid. They're conjugates. And so for the Henderson-Hasselbalch, we have to recognize this type of mixture. When we have this type of mixture, it becomes very easy because what we can do is, this is only if we're interested in the pH. And there are many problems that's all we care about. What is the pH of the solution? So if we're only interested in the pH, then we could use this very simple equation. The pH is equal to the pKa for the acid plus the log of the base to acid concentration ratio. And so what we're going to do, the reason why Henderson-Hasselbalch is such a useful equation is because normally we need the equilibrium. But what we're going to do is we're just going to take the initial base concentration and the initial acid concentration. If we use the initial concentrations here, that means we don't need to set up the ice table. And so people like this equation a lot because it's so simple. And so let's do some examples of Henderson-Hasselbalch acid-base mixture. So if we do acetic acid, HAC, versus HA is just a generic acid. And we're going to go 0.1 molar here. And then we're going to go with acetate, from, let's say, sodium acetate or something. at 0.1 molar. Then if I want the pH, the first is, this is a Henderson-Hasselbalch buffer because HAC and AC minus are conjugate pairs. The other thing we need about Henderson-Hasselbalch is this. The SA must work for the Henderson-Hasselbalch equation to work. Therefore, significant concentrations of both initials are required. So really, the Henderson-Hasselbalch equation looks like this. The pH is equal to the pKa plus the log of the initial for the, if we're doing the conjugate base here, I'm going to say initial plus x because we're using the pKa over the initial, this is going to be A minus, and this is going to be the initial HA minus x. So in order for this to simplify just into the initials, we have to use the SA. So the SA's got to work. Therefore, we got pKa plus the log of the A minus, which is the base initial, over the HA initial. So I'll talk about where this equation comes from later, but that's where the simplifying assumption comes in. And this is the power because there's no reason to use the Henderson-Hasselbalch if we have to use the equilibrium concentrations. If we have to use the equilibrium concentrations, then there's no point in using this equation because we could just calculate it just as easily using the ice table. And so the whole point of this Henderson-Hasselbalch is to skip the ice table and use the initial values. But we're making a guess that the initial values are significant enough such that the assay works. So, for example, let's say my initial value is like 10 to the minus 7 molar HAC and 10 to the minus 7 molar AC minus. I don't need the Henderson-Hasselbalch because do you know what the pH is going to be about? Is there like 10 to the minus 7 molar and 10 to the minus 7 molar, or the pH is going to be about? Well, it's so dilute, it's almost like pure water, and pure water has a pH of what? 7. So the pH is going to approach 7. So it doesn't matter. When you overly dilute things, you're just going to keep watering them down. When I was probably in elementary, I started hearing this. From elementary school to through high school, because I grew up like in a very environmentally conscious area, and they're always talking about pollution. Pollution. The solution to pollution is. Have you ever heard that? Has that been drilled into you? It hasn't. Mm-hmm. Yeah, it was all drilled into us. The solution to pollution is dilution, and so that's not really the solution to pollution, unfortunately. Because that's what, people want to do this with like mercury. They want to just dilute it and spread it all over the globe. But what happens is, then you can't eat, not that I eat swordfish, but I don't want to eat swordfish. Or even tuna. Tuna has potentially high levels of mercury because even though it's diluted, it's concentrated through the food chain. So, unfortunately, the solution to pollution isn't always dilution. But anyway, when we have dilution here, the solution to dilution is pH 7. I mean, when you overly dilute things, it's going to get to pH 7. Does that mean you drink it? No, I wouldn't drink it. I would drink this. This is no problem. Acetic acid, people love it. In barbecue sauce. Barbecue sauce is like a mixture of acetic acid and ketchup, I think. Vinegar, oil and vinegar dressing, that kind of stuff. So I'd eat this. But anyway, what is the pH of this? If I just wanted to know the pH of this, then I don't even have to do the ice table. The pH is equal to pKa. Negative log, that's the power function. So pKa, this is going to be negative log of the Ka. And so the Ka for acetic acid is 1.8 times 10 to the minus 5. And so if I want the pKa, I take the negative log of 1.8 times 10 to the minus 5, plus the log of the acetate concentration over the acetic acid concentration, which is just going to be 1. So this one comes out to 4.74. Actually, I should give one more sig fig on here. It's not exactly 474. And so we'll do 1.8 times 10 to the minus 5, log base 10, 4744. I'm going to carry one extra digit there. This is 2 sig figs. Yeah. So that's what I'm allowed. I'm going to carry an extra sig fig to avoid round off error. Now the log of base 10 of 1 is 0. So this is plus 0. And the pH is 474. I'll just drop the 4, have 2 sig figs there. All right, that's using the Henderson-Hasselbalch. And you can see that that was not that hard. Versus if we didn't use the Henderson-Hasselbalch. Okay, so let's not use the Henderson-Hasselbalch in this case. Versus normal ice method. So what we do is we start off with the strongest acid, which is going to be acetic acid here, and the strongest base present. What's the strongest base present? The strongest base present is acetate. Acetate's a stronger base than water. What forms here? What forms here is acetate and acetic acid. And then we go, hey, there was no change. I should say no change. There's always collisions. And so this is called chemical exchange. And there's always these collisions, but it doesn't lead to anything unique. So are we done here? Unfortunately not. You know, I'd like to be done with this. And so we'd say that there's an NR here, no reaction. But what I have to do is I have to take the strongest acid and react it with the next strongest base. What would the next strongest base present be? Water. So if I do that, I'm going to get hydronium and acetate. So this is my strategy here. All right, so initial I have 0.1 molar here, and then hydronium we're going to assume is 0 and acetate 0. And then this is going to give us our standard 0.1 minus x, here, x, and x. Here. And so Ka is going to equal x squared. I'll skip some steps here, divided by 0.1 minus x. And then we'll use the SA here, and we'll come up with x. This is x squared over 0.1. And so x is equal to the square root of 1.8 times 10 to the minus 6. Times 0.1. I'm skipping some steps just to speed it up. And I get x is equal to 0.00134. And so the percent change here is 1.34%, which is that's better than 4% or whatever. I'm not going to bother with quadratic here. And so this is going to give me 0.09987, 0.00134, and 0.00134. Oops, I made a mistake here. Not 9987, 996. 1308, not 86, 4, 5, 6, 6, 6, 6. 866? Okay. Eight, 6, 6, that's right. So we always double check the equilibrium concentrations. And so I'm just going to take the number I calculate for x here, square that, divide it by 0.099866. 1.802 times 10 to the minus 5. That looks good. So this 1.3% change in the SA didn't severely impact our K here. And so our K is looking good. So now I have to deal with the acetate. So what should I do with the acetate? So I take my acetate and I reacted with the strongest acid present, but now I have to pick the next strongest acid present because acetate plus the strongest acid present was HAC. And so acetate plus HAC gave no change. And so I'm going to take my acetate and react it with the next strongest acid present, which will be water. And what's that going to produce? Acetic acid and hydroxide. Now, you have to have an eye for this. Compare these two steps. So my original step 1 wasn't good. So I was going to do this as my step 1. It didn't work, so I have a new step 1 here. Compare step 1 and step 2. Do you notice something? Do you have an eye for this? I mean, can you catch it? What do you notice about step 1 and step 2? Rebecca? Yeah, one is producing hydronium, the other is producing hydroxide. So should I calculate both and then cancel them out, or what should I do? There's one more thing you need to add to that. You're right, but there's something right before you say that you should state. I already talked about this in prior lectures. They're redundant. They're the same equilibrium. This is the equilibrium between, they're the same thing. HAC and acetate equilibrium. AC minus and HAC equilibrium. So both of these show the equilibrium between the same species. The only difference is one describes it in terms of pH, the other describes it in terms of pOH. And pH and pOH are tied together. And so step 2 would be a waste of time. Step 2 would be going in circles. So this is death loop number 2 for Chem 1B. People going into this loop here. Death loop number 1 was the simultaneous. Death loop number 2 is doing the same equilibrium over again, wasting minutes and not getting anywhere. All right, so really the step 2 should not be this. What's the next strongest? Acid and the next strongest base combo? The next strongest acid-base combo would be H2O and H2O, Kw. But if I'm interested only in pH, would adding like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 additional hydronium to this make any difference? No, so step 2 we'll skip. It should be it should be negligible because we have 10 to the minus 3 And so if we have 10 to the minus 3 and we added, let's say, an additional 10 to the minus 9, it makes no difference because we'd round it off anyway. And so we'd stop here. So the pH is equal to the negative log of the 0.00134. Which comes out to 2.87. But why is it so far off? I got 4.74 with the Henderson-Hasselbalch, and this one I get 2.87. Can somebody find my mistake for me? Take a look at the setups here and then see if somebody can find my mistake. This is a very common mistake because we're not used to doing it. From chapter 16, we're always used to doing this. We're always used to starting with 0.100, right? We're always used to doing that, and we get so used to it, it becomes a habit. Do you see my mistake? I'm treating this as if this were just pure acetic acid, right? Nothing else. But there is something else in there. What was the mistake?
Was it the
Yes, that was my mistake. I cannot start with 0.100. That would be just like acetic acid and water and nothing else. In reality, this is the wrong pH. And my error was because of this. My error was, of course I have acetic acid in there, but I also have acetate. I have 0.1 molar acetate. And therefore, this doesn't come out to X down here. This comes out to 0.1 plus X. And so let's redo this. This is a common ion problem, but I forgot to put the common ion in there. And so what it's going to come out to is, this is not correct. This is going to come out to X squared. Oh, not X squared. Actually, let me fix that. This is going to come out to X, which is let's see if I still have it. Okay, let's see. So I need to redo all these because I forgot the common ion. So this is not correct. This is going to be X times 0.1 plus X divided by 0.1 minus X. Again, I'm going to use the simplifying assumption here. And then I'm going to get X is equal to 1.8 times 10 to the minus 5. Which is going to give me what percent change? Times 10 to the minus 5, 0.18% change. I'm running out of time, so I'm going to skip this.
Are we giving out exams then?
I'll give you your exams back tomorrow. Sorry. So this is a 0.18% change. So then we would just recalculate these values here. And so this is going to be 0.1 minus 1.8 times 10 to the minus 5, etc. 0.8 times 10 to the minus 5. This is going to be 0.100018. This is going to be 0.099972, or 82, sorry, 99982. All right, now let's double check. Our double check worked, but we made the wrong assumption. It's not acetic acid. It's actually a mixture. And so the double check will be 1.8 times 10 to the minus 5 divided by, or times 0.100018 divided by 0.099982. And that comes out to, our K value comes out to 1.800 times 10 to the minus 5. So that checks out. This is a double check with the common ion. And now let's calculate the pH. The pH comes out to 4.744. So it's okay. So anyway, we can save ourselves having to do the ice table by using the Henderson-Hasselbalch. So it's important to recognize the Henderson-Hasselbalch buffer. So I'll have your exams for you tomorrow in lab. I'll pass them back. Tomorrow's lab is qualitative analysis, day 1. So you want to skim through the lab. We're going to start the first part of it. And so not yet, not quite yet. There, I'll get it to you. Yeah, keep reminding. I know. Okay, I'll do it. All right. I'm going to do it right now. Although, I was trying to find online, for that, because he went from paper to online. But I'll do it. I'll start it right now. Okay. And tell your parents that I'm doing it.
And there's a bike that's like coming down, and I'm like, and I'm gonna look into the car, and it's like the most lightest time ever, but I can't see it. I was like, I'll get back to you. And then I looked at his driver's license, and I looked at his badges, and his clothes is so nice, and I'm literally gonna die.
Girl, it's so nice. Like, you should just go with it.
She was like low-key pissed. I would be too, because that was such a stupid.
Oh, God.
That was what I was thinking. But the one time that I'm like trying to be careful, like I said,
No,
Yeah.
Right.
I like differentiate them. Like I was versus
The common ion doesn't have to be weak. It could be a strong acid and its conjugate base. That would not be a buffer. And so the Henderson-Hasselbalch, they both have to be weak. And so there's nothing to differentiate. As long as you have a weak acid and weak base combo that's a conjugate, then you can use Henderson-Hasselbalch. Yeah. You can't have one strong and one weak. And that's the only other option. If you have one strong and one weak, it doesn't quite work. And so just go ahead and use it's just a lot easier to use a Henderson-Hasselbalch if it fits that type of mixture.
I was like, sorry.
No, that's the buffer. No, weak and weak. Buffers are weak acid, weak base combination.
oh wait, sorry, yeah, that's Henderson.
Yeah, Henderson-Hasselbalch buffer. Common ion can be anything. It could be strong and weak, or strong and strong, or it could be anything.
That's what I'm saying, like if it could be anything, but if it was weak, how would I know if that one's supposed to be common ion?
No, if it's strong, if there's anything strong, then you do common ion. If they're both weak, then you would do Henderson-Hasselbalch. If they're both weak. Okay, we'll look at some more examples.
Okay.
Ask me at the beginning of class tomorrow. I'll show you some more examples, or tonight we could look at more examples.
Yeah, maybe tonight.
Okay.
I was gonna say though, because I have like family obligations tomorrow and stuff, so probably cannot make it into class tomorrow.
Okay.
Can I get like an idea what we're gonna do? Because I don't want to miss out. Like I want to.
We're doing qualitative. We're going to do a whole bunch of qualitative analysis, like reactions. So if you miss tomorrow, then you just have to come in extra prepared so you can work quickly to finish. That is catch up. What you can do is you can join a group in the middle, let's say, and then complete the first part because you want to see all the reactions that occur. And so skim through the lab and take a look at it. It's not such an easy lab.
So we're like making something and we like look at it,
Mm-hmm.
and then we just like write down what we observed.
Mm-hmm. Yeah.
And we're doing that for like the entire class.
Yeah. Take a look at the lab write up, the qualitative analysis lab write up, and read through that.
So tomorrow you guys aren't gonna be in the lab.
No, not the computer lab tomorrow. We're going to be in the regular lab tomorrow.
Can I just like look over it and then like try to write it down, and then
Yeah, you can prepare.
Office hours, I could just show you what I read.
No, I mean, you what you should do is you should just write like your procedure out in your notebook so you can work quickly, and you can draw little pictures of it, you know, to help you go through it quickly and see the syllabus.
When I come in next week, I can like be prepared to just write down.
No, you can be prepared to work quickly and catch up that way. Here. So we're doing qualitative analysis day 1. So just read what you have to do is you have to compress day 1 into day 2 and do both day 1 and day 2 in one day. It's possible if you work quickly. Just read through the procedure and just do both in one day. Okay. Yeah. Just come in prepared and you'll be all right.
When wanted me to take the exam today.
You missed the exam?
Yeah, this chapter 17. We talked about it, I think last Monday. And you told me, I think we took it yesterday, but I think we both.
Oh yeah, and then you haven't looked at anybody's
exam?
I mean anybody's exam, right?
No.
You want to take it right now?
Yeah, I was wondering, just because I don't want to miss any other class period.
Okay, because I have to leave at 1. That's the problem for today. Can you do it in 2 hours?
Yeah. Yeah.
I'm sorry? Yeah.
Also, I was gonna say, like, where can I like find the lab manual? Because I don't have to visit it.
On where you can find it?
Yeah, did you post it on?
Yes. You can find it on Canvas. We can take it over here on the computer. Yeah. Well, we can take it here too.
red sky because I don't know what this is today. You're right, is it raining? Or it's not me 85.
That's really random as fuck. Like 85 guys, 85.
Yeah, I'm just like long as this kid.
You know, one of those pumpkins just.
Yeah, that or the XAB, whatever. Jack's still eating yesterday.
Did she?
But she called me. I came to school. I just realized I didn't go to school because everything was locked up.
She just wanted to look at the syllabus.
And then she's like, I was like, you could have checked for this quarter, you could have checked, the syllabus. She's like, I don't know about that.
The school even sent a reminder email.
I guess you just really want to go to school.
You know.
Or imagine like just showing up and there's like no one on campus.
Bye. I do like how he hasn't input any grades.
I don't know, it's like, you go to and you're like, surprise!
So what's my grade?
You just don't know.
I assume I had at least a C. At least.
Yeah, at first I was like, oh, he's doing better this semester, he's actually so like the first semester I was like 10-4.
He wasn't inputting anything.
Yeah.
Okay.
So then I was like, oh my god, he's actually in the grades right as we finished them.
Yeah, I thought he was gonna start doing that. And I was like, oh, never mind. Spoke too soon.
I just want to know when he wants our lab reports. So I was like, we have a lab report.
But we haven't done that.
And we don't know when it's going to be.
Oh, I've done this semester.
Yeah.
Like the last one.
Like, how do we already have 2 formal lab reports?
You have 2?
Yeah.
Oh, because the crystals one too.